This video is a full rundown of everything covered in the fourth topic of the specification of AQA GCSE Chemistry, including all of the different reactions, the pH scale, electrolysis, and the 2 required practicals. I also start off by going through a few things from earlier topics that you do need to know, so if you're feeling super confident with these, skip ahead to 4 minutes. Before we revise the material that was new for Unit 4, I want to go over some information that you learned in earlier units that is vital for success in this unit. If you're feeling very happy with your earlier units, then you can skip ahead. The first thing that we know is that everything in the universe is made of atoms, and an atom is the smallest piece of an element that can exist. So if I take a piece of iron and I cut it in half and I cut it in half down to the smallest bit and I get to 1 atom, well, it's still iron. But as soon as I've got anything that's smaller than an atom, say just a proton on its own, then it's not iron anymore. There are about 100 different elements shown in the periodic table. When you sit your GCSE exams, you'll get a copy of the periodic table that has all the different elements on it. So if you're not sure whether something's an element or not, look and see if you can find it in there. If you can find it, then it is an element, and if you can't, then it's not. Then those elements, if they react together and are chemically combined, or we say bonded, then we have a compound. You need to be able to name compounds from their formulae, and there are lots and lots of examples within Unit 4 where you will need to name salts and so on. There are 2 rules that you should know for your ionic compounds. If there are 2 elements in the compound, then you take the name of the metal, which will be the first substance in the formula, and you leave it just as it is. And then you take the first syllable of the name of the non-metal, so that's ox for oxygen, or fluor for fluorine, or chlor for chlorine, and then you add "ide" to the end. So if you've got a 2-word name with "ide" at the end, it's going to be a compound. Examples of this might include iron oxide, copper chloride, or tin sulfide. And then if it's an ionic compound containing 3 elements instead of 2, we use the suffix or the ending "ate." So again, if you've got a 2-word name and the second word finishes with "ate, you know it's going to be a compound. You're already familiar with sulfates and nitrates like copper sulfate and silver nitrate because these could be salts that are produced in the required practical. But we've also got aluminium phosphate as an example. You could also be asked within this topic to give the formula of a substance using the symbols of its ions. The thing we have to remember with a question like this is that the positive and the negative charges have to match up. You have to have the same number of positive charges and negative charges. So if we say to you that potassium chloride contains K+ and Cl- ions, that's the same number of positive and negative charges, which is good, it's sorted, we can just put them together to make our overall simple formula. But if we have potassium oxide, which contains potassium positive ions, and oxide 2- ions, there's some extra negativity there, so they wouldn't balance. We've got 2 minuses to 1 plus. So the way that we solve that, we can't change the formula of the ions because that's based on where they are in the periodic table. But what we can do is have more or fewer of them. So in order to give me the same number of positive charges as negative charges, I would use 2 potassium ions, so then it becomes K2O. Another relevant idea from the first topic in GCSE chemistry is about separating mixtures. This can be done using physical processes, so things like heating and cooling and filtration that will split up the different parts of the mixture without changing any of the chemicals. It's not a chemical reaction because no new substances have been formed. When we get to the required practical, you should be able to describe using filtration to separate the excess solid from the salt solution that you're going to turn into crystals. From this point onwards, we're now onto new content for Chemistry Unit 4. The first thing that we studied was how metals react with oxygen to form metal oxides. So we could take the name of any metal and say it's reacted with oxygen and then name the oxide. If I took magnesium and I reacted that with oxygen, I would make magnesium oxide, and if I took copper and reacted that with oxygen, I would make copper oxide. The speed of these reactions tells me something about how reactive these metals are. So for instance, copper can stay shiny for a very long time, it doesn't even tarnish. Whereas if I took something like one of the alkali metals, which we know is incredibly reactive, then I can scrape it off with my scalpel to see the shiny silver metal underneath. But within a few seconds, it will oxidize and turn much darker again. So the faster that something reacts with oxygen and changes its appearance, the more reactive it is. Next, if you take a metal and react it with water, you make a metal hydroxide and hydrogen. So just like before, we can take the name of the metal and we can turn this into a word equation. It might help you to remember that water is H2O, it's hydrogen and oxygen. So the formula for a metal hydroxide is going to involve the oxygen and the hydrogen from the water. When you saw this reaction demonstrated with the alkali metals, you saw lots of bubbles. That was the hydrogen being formed. We also saw that the colour of the indicator changed because a metal hydroxide is an alkali. You might find it useful to remember that a hydroxide has a high pH. So for instance, sodium hydroxide, which is a very strong alkali, has a pH of maybe 13 or 14, whereas a weaker alkali like ammonium hydroxide might have a pH of 9. So it's still above 7, it's still a high pH for a hydroxide. We just mentioned the hydrogen bubbles that are released when a metal reacts with water, and we can use those to figure out which metals are more reactive than others. If I gave you these two tubes containing some water and some metal, you could tell me right away that the potassium on the left is the more reactive metal because it's producing more bubbles. You would also notice that the tube on the left would get hotter because it's the most reactive, and this displacement reaction is exothermic. We could also prove that the gas that was being produced in this reaction was hydrogen by igniting it or setting fire to it and seeing that it burns rapidly with a squeaky pop sound. Definitely hydrogen. It's also worth noting that even though we often refer to this reaction as the squeaky pop test, you can't call it that in your GCSE exams and you won't get any credit for using that name. You need to specifically mention setting fire to it or lighting it or igniting it. Now the reactions start to get a little bit more complicated. Metals react with acids to form a salt and hydrogen. But whereas for the first reaction, this always produced a metal oxide, so we could just take the name of the metal and put it in front of the word oxide, and the second reaction always produced a metal hydroxide, the salts produced in this third reaction have different names depending on which acid has been used to make the salt. There are 3 strong acids that you should know the names and the formulae and the salts produced by in GCSE chemistry. So we've got hydrochloric acid, sulfuric acid and nitric acid, and you notice that they've all got hydrogen in them in their chemical formula, which is what makes them an acid, hence the pH scale, the power of hydrogen. Now if I'm trying to make a salt, say if I'm doing the soluble salt required practical, I need to think which acid sounds most like the salt I'm trying to make. So if I'm trying to make calcium chloride, chlor like hydrochloric acid, that's the acid that I'm going to select. Or if I'm trying to make copper sulfate, sulfate sounds like sulfuric acid, so that's the acid I'm going to pick. So if you get an exam question which asks you which acid to use, even if it's not structured as a multiple choice question, even if it's a line that you have to write on, it is a multiple choice question because you only know the name of 3 strong acids, so it must be one of those. So now we're starting to get into the required practical territory. Those first reactions were just with a metal, just with an element, but now we're going to start using an insoluble base that contains that metal. So an insoluble base is something that doesn't dissolve, but it can neutralise an acid. And the 2 examples we should know about for GCSE chemistry are a metal oxide, which is going to react in exactly the same way as the pure metal, except we've now got some extra oxygen. So instead of producing hydrogen, we put that hydrogen together with the oxygen to make water. Or we can use a metal carbonate, which in addition to the metal contains 1 carbon atom and 3 oxygen atoms. So 1 carbon and 2 oxygen produce carbon dioxide, and then the 3rd oxygen atom is what's going to join up with the hydrogen to make more water. You can prove that the gas produced is carbon dioxide by bubbling it through lime water, but to be honest, you're very unlikely to have tried to do this because the amount of gas being produced is quite low, and so it's very hard to get this to work properly. It is worth noting though that the reaction will carry on bubbling until you've used up all of one of the reactants, so therefore it can be a good indication of whether or not your base is in excess. When you're writing about this required practical, maybe writing a method for how to make it, which is a really common exam question, or perhaps correcting a method that they've given you, the first thing that you need to do is to make sure that you've identified and named your 2 reactants. If you don't do this, then you're going to be capped. You're not going to be able to get full marks if you haven't named them at all or if you've named them incorrectly. In particular, it's really common that we see candidates talking about adding the salt that they're trying to make to the acid. So for instance, here they're trying to make copper sulfate and they talk about adding copper sulfate to the acid, and that's not correct. We need to be adding either a metal oxide or a metal carbonate. So as I've just said, this picture is copper sulfate, thanks to my year 10s for the photo. So because it's a sulfate salt, I'm going to use sulfuric acid. Like we just said, look at the name of the salt and think which acid sounds most like that. So I'm going to pick my sulfuric acid and I'm going to pour out a small measure of it. The precise volume doesn't matter for this reaction because we're not doing an investigation. We don't need control variables and things. And I'm going to heat up that acid. And this is to speed up the reaction. And that's particularly necessary if you're using a metal oxide, which can go quite slowly. Then I'm going to add my base. So if I'm making copper sulfate, I could use copper oxide or copper carbonate. So the first name of the salt gives you the clue for which base you need to add. Both copper oxide and copper carbonate would work. There isn't a right answer unless the question specifies you must make a soluble salt from a dilute acid and a metal oxide, in which case you would have to use copper oxide. Or if they say a metal carbonate, you would have to use copper carbonate. But if they just say an insoluble base, then either one is fine. Now I have to add an excess of that base. So we talked about how I was planning to eat an excessive amount of cheese over Christmas, which I did achieve. So I was going to eat too much cheese. You're going to add too much of your base, your copper oxide or your copper carbonate, if we're making copper sulfate here. And the reason you're doing that is to make sure that all of the acid reacts. Because in every chemical reaction, there's always too much of one of the reactants. And we're going to need to remove that if we want pure crystals. And it's much easier to remove excess base than it is to remove excess acid. You just can't do that. You'd have crystals covered in acid and there's no way to wash it off. I would know that I've added an excess of my base when I see or I observe that there is powder, there is solid on the bottom of the beaker, because there's no longer any acid left to react, so some of that solid has been left over. If I was using copper carbonate, I would also see that the bubbling that's produced when the carbon dioxide is released would have stopped. But that wouldn't be the case for the metal oxide, because metal oxides are just going to produce a salt and water, so there's no bubbling to see. Then we need to get rid of that leftover powder, so that's the point at which we filter the mixture. We're then going to evaporate the solution gently using a hot water bath. We can't use a Bunsen burner because this is too hot, it's too vigorous, and so that's not credit-worthy. And we're going to heat it and evaporate the solution until most of the water is gone, but not all of it. Because if we did, we would get boring white powder, what we call anhydrous copper sulfate, rather than our nice blue crystals. I should mention they're only blue because it's copper sulfate. If you were making a different salt like magnesium nitrate or tin chloride, then they wouldn't be blue. So we're going to evaporate most of the water and then we're going to leave it to crystallize. And once we've got those crystals, we can take them out and dry them. In this topic, we talked a bit about reactivity and that order of reactivity or the reactivity series and how we put things into that series by using our observations of reactions, like placing the metal in water or placing the metals in acid. Metals that are less reactive than hydrogen will not react with water, and metals that are more reactive than carbon cannot be extracted from their ores by reduction with carbon, because this is an example of a displacement reaction and only a more reactive element can displace a less reactive element. We mentioned that unreactive metals, which you might think of as jewellery metals like gold or silver or platinum, are found uncombined in the Earth's crust as elements. Think about the California gold rush, where people could literally reach into rivers and find nuggets of gold. They weren't in compounds, they weren't in ores. A more reactive element can take the place of a less reactive element in a displacement reaction, but this cannot happen in reverse. Carbon is used for displacement of metals like copper or iron because unlike highly reactive metals like potassium, which could still displace them, it's cheap enough for this to be financially viable. You should be able to identify within a reaction which element has been oxidized because it's lost electrons and which has been reduced because it's gained electrons. And we use the mnemonic oil rig to remind us of this. So oxidation is loss, reduction is gain. You should also be able to show these processes using symbol, ionic, and half equations. If you think about just one element at a time, magnesium here goes from being magnesium atoms with no charge to magnesium ions with a 2+ charge. So because it's positive, that tells me that it's lost negative electrons and therefore it's been oxidized. Meanwhile, the hydrogen in the acid goes from being hydrogen ions with a positive charge to hydrogen molecules with no charge. So the hydrogen atoms have gained electrons, they have been reduced. So the first line here is my symbol equation. It shows me everything that's involved in this reaction. The second line is the ionic equation. We've removed what we call the spectator ions. So the chloride ions are in the hydrochloric acid at the start, they're in the magnesium chloride at the end, but they haven't changed. They're Cl- on both sides, so we've just skipped them out. That's what we do for an ionic equation. We skip out anything that's not actually taking part. And then my bottom two lines are my half equations, and this is only going to apply to one of the elements in the reaction. So my first one, I've got magnesium splitting apart to make magnesium 2+ ions and 2 electrons. And then for my second one, my 2 hydrogen ions are gaining 1 electron each, so 2 in total, to make hydrogen. Next, we cover the pH scale. You should know that it's called the pH scale because acids contain hydrogen, which they release when they dissolve in water to form aqueous solutions as hydrogen ions or H+ ions. This process is called dissociation or ionization. Likewise, soluble bases called alkalis release hydroxide ions or OH- ions when they dissolve in aqueous solution. If you're struggling to remember the formula of hydroxide ions, it may help to remember that these and the hydrogen ions join together to make a water molecule. So if you remember the H+, then the OH- is just what's missing from water. The pH scale goes from 0 to 14. The high numbers are for the hydroxides, those alkalis, whereas the low numbers are for the acids, and pH 7 is neutral, at least at room temperature. We mentioned the ions that are released by acids and alkalis when they dissolve. These can join together as part of a neutralisation reaction, and we can represent them with this ionic equation, which is the same for any acid and alkali neutralisation. The pH scale is an exponential scale, not a linear one. So this means that for every single number you move on the pH scale, the concentration of hydrogen ions changes by a factor of 10. And actually it's a negative exponential scale. So as the pH increases by 1, the hydrogen ion concentration drops by a factor of 10. So say if we went from pH 1 to pH 4, then that would actually be 1,000 times less hydrogen ions in the same volume. Finally, for the pH topic, you should know that strong acids like hydrochloric acid, sulfuric acid, and nitric acid are completely ionized in water or in aqueous solution. In other words, when they dissolve, every acid gives up its hydrogen ion, and this leads to a comparatively low pH. Whereas our weak acids, citric acid, ethanoic acid, and carbonic acid, are only partially ionized or slightly ionized. So many of them hang on to their hydrogen ions. This means if we have two solutions of a strong and a weak acid of the same concentration, the weaker acid will have a higher pH, because even though the concentration of the acid is the same, the concentration of the hydrogen ions, which is what controls pH, is much lower. Finally, in Unit 4, we have electrolysis. This is a pretty big subject, and if you're unsure, I'd recommend looking up my separate electrolysis video. Electrolysis means splitting ionic compounds, called electrolytes, into their elements using electricity, specifically DC electricity. The electrolyte must be either melted or dissolved to allow the ions to move. Don't forget, within electrolysis, we are always talking about mobile ions, never delocalized electrons. We call the positive ions cations and the negative ions anions. These ions move in response to charge, with the positive cations being attracted to the negative cathode and the negative anions being attracted to the positive anode, because opposite charges attract. If these ions have colours, then this may mean that you can monitor the progress of the reaction by seeing the different coloured ions moving. When the ions reach the electrode, electron transfer takes place and the ions are discharged. So that means they stop being charged and are turned back into atoms that are neutral. If you're taking the higher tier exams, then you should be able to express these changes using half equations. So here an aluminium 3+ ion gains 3 electrons to turn it back into aluminium atoms. We're always aiming to have neutral uncharged atoms, so positive cations will gain the same number of electrons as the charge on the ion. And this can be determined, if you haven't been told in the question, by which group the element is from. So aluminium is from group 3, therefore it makes 3+ ions. Gaining electrons like this is an example of reduction. So we say that the aluminium ion has been reduced. Meanwhile, at the other electrode, 2 oxide ions, and remember we need to be referring to ions by their proper names, particularly those negative ions, so this is oxide ions, not oxygen ions. Those 2 oxide ions lose 2 electrons each and therefore leave a neutral oxygen molecule and 4 electrons overall. This is an example of oxidation because oxidation is loss of electrons. You should specifically be able to talk about the extraction of aluminium from aluminium oxide as an example of an economically important electrolysis reaction. In this reaction, cryolite is added to the aluminium oxide electrolyte to lower the melting point and therefore allow the energy costs to melt the aluminium oxide to be lower than they would be otherwise. It's a lot like salting the roads to prevent water from freezing at such a high temperature. Over the course of this reaction, the aluminium ions will move to the negative cathode and the oxide ions will move to the positive anode, and both of these will be discharged. This is a very expensive process, and we only use it because we have no other options. Aluminium is more reactive than carbon, and therefore it can't be extracted by reduction with carbon. And also, similarly, it's more reactive than hydrogen, and therefore we can't extract it from a solution instead of a melt, in other words, an electrolyte that has been heated up until it turns into a liquid. So this process is very expensive for 3 main reasons. One is that even using the cryolite, the energy costs in order to melt the aluminium oxide are very, very high. Secondly, we need electricity for this to work, and so there's an energy cost associated with that. And thirdly, the carbon anodes, the electrodes, keep wearing away and needing replacing. So these anodes are made from graphite, which is a form of carbon that can conduct electricity because it has delocalized electrons. Carbon is obviously relatively inert, so it tends not to react with the electrolyte, and also it's quite cheap. However, when the oxide ions are discharged at the anodes, very hot oxygen gas is produced. And due to the high temperature, this is able to react with the graphite electrodes, producing carbon dioxide and gradually wearing them away. So they need replacing almost every month. Finally, for Unit 4, you need to discuss the electrolysis of substances that have been dissolved to make solutions rather than melted. This is a good way to extract metals that are less reactive than hydrogen. There's also a required practical associated with this topic. So when we think about a solution, that means something that has been dissolved in water. So we're going to have the ions from whatever it is that we're trying to electrolyse. So say maybe that could be, if it was copper chloride, we would have some copper ions and we would also have some chloride ions, but we're also going to have the ions from the water. So that's hydrogen ions and hydroxide ions. And all of these are going to try to move to the relevant electrode. So the positive copper ions and the positive hydrogen ions will both move to the negative electrode, and then likewise the negative chloride ions and the negative hydroxide ions will both move to the positive electrode. But only one of each of these ions is discharged, and therefore we only have one product at each electrode, and the remaining products stay in solution. So our first rule is that at the cathode, the most reactive cation stays in solution. So this means that the only cations that can be discharged are hydrogen ions, in which case we would get hydrogen gas, or metals less reactive than hydrogen. And a good way to remember these, although you couldn't describe it like this on the exam paper, is that they are metals that are good for making jewellery. So copper and silver and gold and platinum. They can be extracted from solutions using electrolysis. Anything more reactive can't, and you'll just produce hydrogen. Then my second rule is that at the anode, if there is a halide ion, so that means something from group 7, so that could be a chloride ion or a fluoride ion or bromide or iodide or astatide, those are preferentially discharged. In other words, we do make them. So in this situation, we would make chlorine gas. If there aren't any of those ions available, then it doesn't matter what other ion there is. It could be something from group 6, it could be a compound ion like a nitrate or a sulfate or something. Whatever it is, everything else is lower in the hierarchy than the hydroxide ion. So that hydroxide ion will be discharged, whatever the other anion is, and therefore oxygen gas will be released. You should be able to describe these processes with half equations, and I would particularly pay attention to the one for hydroxide ions because it's probably too tricky to figure out under pressure in the exam, so it's definitely one that's worth memorising. Thank you very much for watching, and I hope you're now feeling fully prepared for the 4th unit of AQA GCSE Chemistry. If you did find this video useful, then don't forget to like and subscribe for more GCSE Science revision videos coming soon.